Hi, welcome to the session of Industrial Protocol Gateways, a deep dive of Moxa MGate 5105. My name is Philip Wing. I'm Senior Threat Researcher in Forward-Looking Threat Research Team of Trend Micro. This study is a teamwork with Marco Bagducci, Charles Baring, Ryan Flores, Rainer Fossler, and Luca Bongiorni. So first of all, thank you for having us here. As a team has already delivered several talks around the topic. This talk is intended to be a deep dive of Moxa MGates. So if you want to have a high-level overview of protocol gateways, please refer to my previous talk in RSA, Asia Pacific, and Japan. And if you want to have a deep dive of real-time gateways, please refer to Marco Bagducci's talk in Black Hat US. So we have decided to do a thorough study of protocol gateways in terms of translations. We want to make it cross-vendor, so everyone choose a vendor that's representative in the world. Since I am Taiwanese and Moxa is a Taiwanese vendor, so there's no brainer for me to choose Moxa. So here is how it looked like when it arrives. So that's the carton box. When you open the carton box, you see the quick installation guide, user manuals, and a serial console cable, and the MGate protocol gateway itself. It's quite minimalistic. And here's how the front panel looks. So from the front panel, you see two power LEDs, one red LED. You have an LED for a Modbus and one for Ethernet IP. There are two Ethernet jacks and one console, and one 9-pin Modbus connector for both Modbus over RS-232 and RS-485. And on the back panel, you have two power inputs. The power input ranges from 12 volts to 48 volts. You have one relay and one slot for micro SD cards. So if you insert the micro SD card before the device boots, the device would dump the whole database as a backup to the micro SD card. So actually, you get everything from the dump. And this is not what we want to do because we want to study remote vulnerabilities and the translation errors of the device. So that we will just put this topic aside. On the bottom, you see a label, and there is a production serial number on the label. And luckily, this time, we don't have a serial number that works as a single key to everything. So it's pretty nice. And then we open up the lid. This is one of the bad habits that whenever we get something, we just open it up. And luckily, there is no pressure button inside the lid that erases the double EEPROMs and firmware once we remove it. And on the circuit above, you see a power isolation circuit. That's pretty neat. And on the lower side, you see something like a JTAG. We will take a closer look. Let's zoom in. So here are 4 pins that's used as a most likely an UART for internal debugging. And you have 16 pins here, just like a JTAG. We didn't dig deeper into these connectors because, if you want to touch the internal circuit, you have to open up the lid, which means you are in proximity of the device. And that's out of the scope of the study, so we just leave them alone. And Moxa comes with a telnet interface that's very minimalistic. You just log in with admin account, admin and Moxa. And it's a very good reminder that the Moxa tells you you have to change the default password because default password is known by everybody, so that's not secure. It's a really good reminder. Then you have a very simple interface that you can change some minimal things. And luckily, all the input string are sanitized, which means that if you just input a very long A's, there's no segmentation fault, no hang-ups. So that's pretty good. And Before I can go further, allow me to explain a little bit how data station types of protocol gateway works. So there used to be several routines working at the same time, but we can just make it simpler by thinking there are two routines. The first routine is a parser. It parses the input and it just reads the inbound packet and parse the commands and read the input and put it to the internal memory. And the second routine scans the internal memory and see if any value has been changed. Then it checks the I/O mapping table and trigger the commands that fits the change of the internal memory and sends the translated output to Modbus slaves. And this is a typical interface of Moxa MGate web user interface. You can enable and disable the consoles, and at the very bottom you see there's one Moxa command, which we will come back in a little bit. And the first thing you have to decide for a protocol gateway is that you have to decide from which protocol you want to translate to which protocol. So here is an example of translating Ethernet IP to Modbus RTU. And actually, you can translate from Ethernet IP to Modbus TCP, or Ethernet IP to Modbus RTU, or Modbus TCP to Modbus RTU, anything you want. And actually, Moxa has a very, very interesting implementation of Ethernet IP, which we are not going to talk about today. That might be subject to the next study. And today we are going to talk about Modbus TCP to Modbus RTU. So when you have decided from which protocol you want to translate to which protocol, the first thing you have to do is to design a I/O mapping table. On the screen above, you'll see a table of Modbus commands. That's the functions that you want to trigger when anything has been changed. So we have put function 5, write coil, function 6, write register, function 15, write multiple coils, and function 16, write multiple registers. And the table at the bottom shows that whenever the internal address, for example, internal address 0 is changed, it triggers command 1. And when internal address 16 to 17 is changed, it triggers command 2. And you might have noticed that there's some overlapping addresses here. For example, if you change a value at internal address 16 to 17, it triggers both command 2 and command 4. You might think it's nonsense, but actually it's not. It's like if you have two slave devices that want to receive the same settings at the same time, you might have assigned two separate commands, one for each slave device. So after proper configuration, you can set up a test bed just like this. You might have noticed that the power is actually a 12-volt power converter that's off the shelf that I have torn apart from somewhere else. And I have a very Hackaday style power jack that's connected to a two-way relay that's connected to a Raspberry Pi running Bullfuzzer. And Bullfuzzer is sending packets via the Ethernet cable to Modbus TCP input. And then Moxa translated to Modbus RTU that we read from with the USB to serial converter that you see above. So Bullfuzzer is a very powerful and very adaptive fuzzing framework. It's open source and it's really, really useful. We have extended it and implemented many fuzzing tests. For example, we have changed the packet length, the packet size, and we have introduced the trailing garbages, everything. And Moxa has a very robust inbound parser that even with these invalid lanes, invalid CRC, invalid package, modified packets, and the trailing garbage, the parser didn't hang. So that's quite robust. That's really good. But however, when I check the I/O mapping table and the internal memory by using the I/O data view function that Moxa has provided on the web user interface, things didn't look that good. Why is it so? It's like, if you have noticed that we have only configured Moxa address, Modbus address 4x01 to 4x04 and 4x09 to 4x0456. So that's the area that's like in the rectangulars. Those addresses outside the red areas are actually changed and filled with random data. So you might think, what's going on here? What's wrong? And why is the internal address that's not defined by our commands is also filled with data? So there must be something wrong here. And actually, I'm quite confused by 4x because according to the manual, 4x01 means the internal address starts from 1, and 0x something means the internal address starts from 0. So you might think 4x01 equals 0x00, right? But actually, no, we don't really know what 4x stands for here. So we decided to just input the data one after another and see what's going on. So you can use function 5 just like to turn on and off a switch. We try to turn address 0 on and off, and you see the RTU address 1 is turned on and off. That's good, right? But when you turn switch 1 and switch 2 on and off, you are still seeing RTU address 1 being flipped on and off. And then you just increment the address all the way to 10, 11, 13, 12, and 13. And you have noticed that, wait, well, why is function 6 triggered? We are like, we're just flipping the bits on and off, and it should have nothing to do with function 6, which has to deal with the holding registers. So here's actually how it works. We have finally figured out this is the normal operation. So you first define all the commands and which function it has to trigger when the data changes. Then you define a range of internal memory that routine 2 is going to monitor. And when the data within the monitored area has been changed, it issues and triggers the command. So in a normal operation, you just issue function 5 address 1 to turn the coil on. And then the internal memory address 0 is changed from 0 to 1. And then the scanner, the routine 2, detects the change in internal address 0, and it triggers command 1 and sends the command 1, that is function 5, say the AD1 to address 1 and quantity 1, etc. So there might be a way to misuse it. For example, if we are writing to a coil or a switch that's not previously defined or is out of bounds, it's actually divided by 8 because 1 byte is 8 bits. So 1 byte of internal memory actually holds 8 switches. So you can just turn on a non-existing switch and change the value anywhere in the table. So anywhere in the internal memory. And whenever you have an internal memory that's covered by, for example, command 3 or command 4, you are triggering command 3 or 4, depending on which address you have changed in the internal memory. And maybe you might think this is not a big deal because this is everything we have defined. So let's look at the demo. So we have used the VT scaler to mock an HMI, and you see there is a critical threshold that you can usually change from a holding register. And of course, you want to set a firewall that prevents the holding register to be changed by unauthorized persons. However, anyone can just use function 5 to flip a bit in the holding register, it's something you might not block. For example, we are writing address 22 here. So 22 is the leftmost most significant bit of the holding register, and it's changed to 1800 degrees. That's a very high degree, and your things might melt in production line. Or we can even change its negative value because it's a signed value. So the leftmost bit setting to 1 means it's a negative sign. This would be really, really bad. And this is, and we're not stopping here. So from the firmware downloaded from the Moxa's website, we are able to decrypt the firmware. Even though the firmware is encrypted, you can actually Google and find a way to extract the AES key that you can use OpenSSL command line to decrypt it. And just use Springword, it's possible to extract everything in the firmware. That way, we have learned that it's actually running BusyBox 1.24.2, which has several non-vulnerabilities. We have tested Moxa with these non-vulnerabilities, but failed. We have also extracted the default password for root user admin, and we use a John the Ripper to brute force the password, and of course the password is Moxa. So that didn't really help. And maybe you think it's possible to log in as root, but root has a default shell to bin false, so we cannot really use it to log in. And luckily, Dov Chu, a really good colleague of mine, has helped figuring out that whenever you have logged in as a normal user, you don't even have to be an administrator. It's possible to just go to the ping test page and type a semicolon busybox telnetd to open up the port that allows you to telnet in, and it doesn't ask for any credential, and you got a root shell. It's really nice, but the problem is that you have to log in first. And it's possible to bypass the login with a session ID if you know the session ID, which means you either have to sniff the network traffic and intercept the session ID, or you have to make an educated guess and brute force the session ID, which we will talk in a bit again. So since most of the field engineers are using Windows-based program to manage MGate, so this is the MGate manager that Moxa provides for Windows users. And if you are a field engineer, you just plug a network cable onto your laptop and run MGate manager, and you click on the scan button. The scan button would send a UDP broadcasting packet, so that if there's an Moxa MGate device on the local area network, it returns the name, the serial number, and description of the Moxa MGate portal gateway. And everything is transmitted over UDP port 4800 and TCP port 4900. Most of the things are not encrypted, so we can read them just as clear text. And that is the Moxa command. So we decided to use Scapy to try to figure out how Moxa command works. So we have identified the packet format. It's what you have seen above. The format is like 2 bytes of commands, like 0100 is used to identify the device, and the respond is OR with 0x80, and it's followed by the length and the sequence number. And the sequence number is followed by 6 bytes. I don't know why it is there. I don't know what that means. Then it's followed by the MAC address of the Moxa device that you want to talk to. Then it's followed by the data itself. So we have figured out that there's something like a keep alive or filler that if you open the MGate manager, it just sends the keep alive packet over and over again. And when it queries the device name is 1000, that's a command. So, it's not really possible to brute force, it's not possible to just record for a very long time and study all the commands. So we decided to ask our best friend, IDA Pro. This is what IDA told us. So this is the Moxa commands that's supported by Moxa MGate 5105. You can actually set admin password, get peer name, set time of day, set console, upgrade firmware, etc. if you know how to issue the commands. That's really useful, right? But the problem is that most of these commands are privileged commands and requires you to log in as admin in advance. So how does it do? So for example, you want to log in, or any field engineer wants to log in. The first thing is that it pops up a dialog box asking you to type the username and password. The username is what you see here. It's padded with 0s to 8 bytes, sending in clear text. Then the password is actually a nonce conjuncted with a password, and you use MD5 to hash it. So what's being transmitted over the Ethernet is the MD5 hash. And how do we know that? It's because our very good friend IDA Pro told us. So this is how things look like. Moxa MGate manager uses 0001 command to get a nonce, and 4 bytes of nonce is returned. Then it uses password conjuncted with the nonce. Then it calculates the MD5, and the MD5 is returned to authenticate this login. And so the thing is that if the nonce is really random, then we are game over here. We have to find another way to exploit another thing. But when God closes the door, he opens up the window. So here's the window. We have reversed SDS DSC ID and noticed that it's calling rand to get a random number, but there's no srand for the seed. It means that each time when SDS DSC ID is restarted, or each time you reboot the device, the nonce is actually repeating itself, and it matches our observation. So it implies that you can just intercept as long as you can and accumulate enough nonces, and you can just send over the encrypted hash. You can do the replay attack, and there's no problem because the nonce is repeating itself. You will eventually get the right encrypted password. And there are several suggested ways to get a random number out of a Linux box. For example, not really recommended is the srand time null. It's because the time resolution is limited. So if you have a lot of threads doing this srand time at the same time, you get the same seed, and that's not very good. You can actually get the random seed from the DEV random, but the problem is that if you are doing it really fast, there might be some entropy issues, and you can get it from DEV random, but it might block the thread. So since Linux 4.8, a new algorithm called Cha-Cha 2.0 is introduced in urandom, so that it ensures that you can get a really good random number each time you read something from DEV urandom. So that's really good, but the problem is that embedded devices might not be running such a new Linux kernel. So anyway, Moxa doesn't call srand before calling rand, and that's not a good practice. And when we were sniffing the traffic, we have noticed something very interesting. You can see the table on the right-hand side. It's actually transmitting mysterious numbers in ASCII. And you might think, what can that be? So we reverse engineer a little bit more, and we found that, okay, so 0100 is a fixed value, followed by a length of original file. And you have actually the AES key in the beginning of the dump. So this encrypted configuration is actually being sent from Moxa device to MGate manager, so that field engineer has all the configurations that he or she can change in the graphical user interface. And then when the field engineer closes the program, Moxa MGate manager would upload the database again in the same format. So all you have to do is just to Wireshark or T-Shark it and save the PCAP. And we have even written a Python script that's called Scapy to parse the PCAP and reassemble the MGate dumps. We're calling the dump MGate 5105.ini because it's exactly the same thing that you can find on an SD card. And one of the problems is that we don't know how to decrypt the file. Not really, we don't know everything about it, but we have tried to re-implement the function in PyCrypto, but we failed to do so. So in order to save some time, we just wanted to load Moxa's share library and use it to decrypt the file for us. So how to do that? Cross-tool ng is a very useful utility that you can use to prepare the compile time runtime. So we use cross-tool ng and with ARM unknown Linux GNU EABI to reconstruct all the compiling environment. And we have a tiny proof of concept C program that you can just cross-compile and use QEMU-ARM to run it. So this is the actual program. It uses DLOpen to load libconfig.so from Moxa's firmware, and it's finding the decrypt config v1 AES from the symbol table, load the address to a function pointer, and we're calling this function pointer with the MGate 5105.ini that we have just dumped from the PCAP file, and it will be decrypted and saved to decrypted.tgz. And this is what's being decrypted. It's config data along with a lot of database, and the database is in SQLite format. So just use ordinary SQLite 3 to you can dump the whole database and see what's going on inside. You have the password, shadow, and SNMP configuration, and even an SSH key that I don't know where it's used in. So there are good days, there are bad days, and this is Hack in the Box, so we're not only talking to you about the good days. And in order to learn how Moxa MGate 5105 works, I have done a thorough study of the booting sequence. And that's not really helpful, to be honest. And first, it runs a auto login with a console program. But the console program requires you to insert the console cable. So you have to be within the proximity to the box. So that's not what we want to do. So next, there's RCS that's it's basically making the configuration directory and extracting default settings and then mounting the right partition, user configuration partition, and gets a serial number, starting configuration services, and then running the SDSCID, our good old friend. Then it's running mmccd, which is a daemon that detects the insertion of an SD card. So if you have the SD card inserted before this step, it's dumping the database. So it's mounting it first, then dumping the database to the SD card. And if you have configured it, it's also saving the log files onto the SD card. So then it began to initialize the network configurations like IP tables, SNMP, LLDPD, etc. And the LLDPD is probably something that we have found on the GitHub. Then it's initializing the DHCP for IP address. Then it's running an event D. Event D might be a Moxa internal daemon for event loops. So there are several Moxa daemons that's possible to pass IPC communications by event D. We're trying to exploit it here, but we didn't make it. Then there is a telnet D that takes our telnet to port 23. It's a busy box. And there's something very interesting. There is a telnet 6000 that listens to a UDP packet to port 6000. It's actually calling command the system call to run a UTCP dump command that has a %s. And whenever you have a system and a %s, there might be a chance to exploit it, but no. The inputs are fixed, so it's not vulnerable. And it's running go-ahead web server 2.1.8, so we have Googled it a bit and learned that it's vulnerable to CB 2017-17562. So we have tried it, but not vulnerable. So maybe Moxa has already patched it. We have studied a little bit about the lab protocol, and we have found one undocumented protocol supported or not supported by this protocol gateway, but we cannot exploit it. And we have found two hard-coded keys in labconfig.so. The first key is Moxa Technology DN, and the second key is Moxa Tech DN. Actually, the second key is used in the procedure of encrypting the password hashes. So this is how we inspect it. You first pad the hard-coded key Moxa Tech DN to 16 bytes. Then you pad the admin password to 16 bytes as well. You'll take the SHA-256 of Moxa, the default password, take the digest, and take the first 60 bytes of digest, make it hexafied. Then you use it then you use the hard-coded key to AES encrypt it. Then you get a binary. So that matches our observation in the very beginning of the MGate 5105.ini file, the database dump file. Why I'm saying it's failed because there's no way to implement MGate AES encrypt and AES decrypt with a PyCrypto. We have tried several times and failed. So maybe Moxa has their own implementation. So if you cannot make all protocols from scratch, you are not really doing anything. And we have noticed that there is a user T struct, a C structure that's storing username, system clock, and the password, and session ID, etc. Session ID is the session ID that we were trying to brute force when we have found the ping test vulnerability. So what I have done is to first log into the root shell, run the FTPD so that I can download anything that interested me. And then I have uploaded GDB server onto Moxa and have it running. Then use PS to find the PID of the web server. Then it's possible to just cat prog PID and the maps to find where the heap is. And I have uploaded a short program that dumps the heap from me into a file. And the heap is on this example, the PID is 1020, and the heap followed by the heap. So it's dumping the heap, and here is the hex dump of the heap. So you can actually see the structure. Each user structure takes 840 hexadecimal bytes. The I+4 is the username, so admin, and I+24 is the system clock. The system clock is the second from the system since the system boot. So that whenever you reboot the system, it's 0, and then 0, 1, 2, 3, 4, etc. And the session ID is the MD5 digest of the system time. So, wow, that's good, because if I just restart the system, for example, I can use a command to issue the reboot commands over Modbus TCP. That's because there's a magic packet documented in the manual. Then the system time got reset to 0, and you can make a really quick guess by calculating the MD5 of 0, 1, 2, 3, 4, right? But no, it's not working. So the problem is that Moxa is taking 128 bytes out of the stack. The system clock is in the very beginning of the stack, and there's some initialized trailing garbage in the stack, so that there's no way to calculate the right MD5 without guessing the trailing garbage. And the trailing garbage is randomized whenever you reboot the system, it's randomized, not because Moxa wanted to randomize it, but because the stack is not initialized, the memory is not zeroed out. So if Moxa had obeyed some good programming rule that initialized the stack before their usernet, maybe we have the chance to brute force it. So, Moxa is really lucky here. And this is another failure. So, as a reverse engineer, we really like to see sprintf with %s. Sprintf means there's a chance to buffer overflow, and %s means you have the chance to control the input. And even though Moxa is using smprintf here, that's actually not smprintf because the length is actually taken from the input. So they are, it's equivalent to doing an sprintf without the real length of the buffer. So, promise me, don't use smprintf this way. However, after a very careful inspection of all smprintf calls within the code base, I'm not able to identify any place that I can control to cause a buffer overrun, so failed. And this excerpt of code is the DSCID, our old friend, that's reading a packet, a UDP packet, and put it to buff2. The problem is that you cannot send a really long UDP packet. It has a maximum length of something like 1,500 bytes. And after this receive, Moxa is also testing the length of the UDP packet. So there's no chance to run a buffer overflow of it. Better luck. So all in all, this is a summary of the vulnerabilities that we have identified. We have followed the ZDI's responsible disclosure and reported all the vulnerabilities back to Moxa. And Moxa has either fixed it or provided a mitigation plan to the customers. We really want to express our gratitude to Moxa for their timely manner and prompt responses. They are very responsible, and they have fixed everything, and that's good. So here's the talk. Thank you again for attending this talk. Should you have any questions, feel free to drop me an email or see you at Hack in the Box Discord channel. You can ask any questions you want. I'm happy to answer. And if you have some spare time, please scan the QR code on the right-hand side. It's a link to our white paper, and you can find more portable gateways in depth in the white paper. So thank you again, and have a good conference.